Today we will learn about gas laws. Our question of the day is, what is the relationship between pressure and volume, volume and temperature and pressure? At a constant temperature, as pressure goes up, volume will go down. This is because they are inversely related. We use Boyle's law to show this mathematically. P1V1 equals P2V2. So the starting pressure times the starting volume is equal to the final pressure times the final volume. Pressure and volume are inversely proportional. As volume goes up, temperature also goes up at a constant pressure. We use Charles' law to show this. So V1 over T1 equals V2 over T2. That means that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. Volume and temperature are directly proportional. When the volume is constant, then when pressure increases, temperature will also increase. We show this using Guy-Lusac's law. P1 over T1 equals P2 over T2. The initial pressure divided by the initial temperature is equal to the final pressure over the final temperature. This means that pressure and temperature are directly proportional. The combined gas law is what results when you combine Boyle, Charles, and Guy-Lusac's laws. It is P1V1 over T1 is equal to P2V2 over T2, or you multiply the initial pressure times the initial volume and divide by the initial temperature. This will be equal to the final pressure times the final volume over the final temperature. If any of these three variables is held constant, you can remove it from the equation to get one of the three laws that make it up. It is very important that you realize that temperature is in the denominator of this equation. So if the temperature was 0, the equation would break because you cannot divide by 0. It would be undefined or an error. In order to eliminate the possibility of dividing by 0, temperature must always be changed to Kelvin. As a reminder, to go from Celsius to Kelvin, you add 273. If you are trying to get back to Celsius, you will need to subtract 273. This is because Celsius can be negative, but Kelvin cannot. It is the absolute temperature. Now let's consider molar volume. Regardless of the identity of the gas, a mole of gas will occupy 22.4 liters of volume at standard temperature and pressure. We call this amount, 22.4 liters, the molar volume of a gas. Since the volume of a gas does not depend on its identity, neither will the pressure. In a container of unreacting gases, the total pressure exerted will be equal to the sum of the pressures of the individual gases. This rule is called Dalton's law. So let's consider a few different gases. Let's say nitrogen is exerting 78.1 kilopascals of pressure. Oxygen is exerting 20.9 kilopascals. Water vapor is exerting 1.28 kilopascals. Argon is exerting 0.97 kilopascals, and carbon dioxide is exerting 0.05 kilopascals. Then, when you mix them all together into a single air container, you will see that it has a total pressure of 101.3 kilopascals. This is because the pressure of any gas mixture is equal to the pressure of the individual gases added together. Now pause the video and try the show what you know questions. After you have finished, you may resume. Let's look at number 1, the total pressure in a container of two inert or non-reacting gases is 2.5 atmospheres. If the pressure of the first gas is 0.9 atmospheres, what is the pressure of the second gas? Well, let's use Dalton's law so that the pressure of the first gas plus the pressure of the second gas will be equal to the total. That means that we can subtract 0.9 from 2.5 and get the pressure of the second gas, which is 1.6 atm. Now let's consider number 2. A quantity of gas has a volume of 100 milliliters at a temperature of 200 Kelvin. The temperature of the gas is raised to 350 Kelvin while the pressure remains constant. What is the new volume of the gas? According to Charles' law, the initial volume of 100 milliliters can be divided by the initial temperature of 200 Kelvin, and the final volume, which we are looking for, can be divided by the final temperature of 350 Kelvin. That means that you can multiply both sides by 350 and get the new volume. This volume is 175 milliliters. We were able to use the temperatures as given because they were given in Kelvin. In example 3, a sample of gas in a rigid cylinder has a temperature of 350 Kelvin and a pressure of 175 kilopascals. What is the pressure going to be when the gas is cooled to 273 Kelvin? Well, the temperature is already in Kelvin, so we don't have to worry about converting it. Instead, we can plug our values directly into Guy-Lussac's law. So pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. This means we are going to take our initial pressure of 175 kilopascals and divide it by our initial temperature of 350 Kelvin. Then we're going to multiply this by 273 Kelvin to get our final pressure. This pressure is 139 kilopascals because our initial and final pressure have to have the same units. Now let's consider example 4. The volume of a gas changes from 15 milliliters to 27.8 milliliters at a constant temperature. What will be the new pressure of the gas if it began at 1.3 atmospheres? Well, according to Boole's law, P1V1 equals P2V2. So our initial pressure of 1.3 atmospheres can be multiplied by our initial volume of 15 milliliters. We can then divide by 27.8 milliliters to get a final pressure of 0.7 atmospheres. Now let's consider example 5. A gas at 50 milliliters, 273 Kelvin, and 105 kilopascals has a temperature rise to 300 Kelvin and a new volume of 70 milliliters. What will be the new pressure? Well, since we are looking at pressure, volume, and temperature, we are going to use the combined gas law. P1V1 over T1 is equal to P2V2 over T2. We will multiply our initial pressure of 105 kilopascals, our initial volume of 50 milliliters, and divide by our initial temperature, which is 273 Kelvin. On the other side, we don't know pressure, but we can take our final volume of 70 milliliters and divide by our final temperature of 300 Kelvin. We can then solve for the unknown pressure, and we get 82.4 kilopascals as our final pressure. In number 6, a gas at 2.8 liters, 273 Kelvin, and 2.4 atm is cooled to 250 Kelvin, and the pressure increased to 2.6 atm. What will be the new volume of the gas? Well, once again, we are going to set up our combined gas law, and when we solve for the unknown volume, V2, we are going to get P1V1 times T2 over T1 times P1. When this is multiplied out, we get 2.4 liters as our new volume. Next, consider question 7. Helium and neon are mixed in a rigid 5-liter container. The pressures of the helium and neon, respectively, are 65 kilopascals and 80 kilopascals. If the mixture began at 273 Kelvin and the temperature is increased to 300 Kelvin, what will be the new total pressure of the gas mixture? Well, according to Dalton's law, the total pressure of the gas mixture is 65 plus 80, or 145 kilopascals. Since the container is rigid, the volume will not be changing. The temperature rises from 273 to 300 Kelvin. Since both are in Kelvin, we do not need to bother about converting, and we can use Guy-Lussac's law directly. We solve for P2, the new pressure, by taking P1 divided by T1 times T2. So 145 divided by 273 times 300, which will give us 159 kilopascals. The final question says a mixture of water vapor at 100 kilopascals and carbon dioxide with a pressure of 50 kilopascals are in a 100 milliliter container at 330 Kelvin. If the volume of the container is doubled and the temperature is held constant, what will be the new total pressure of the container? So our temperature is constant, which means we can use Boyle's law. P1V1 equals P2V2. So to get the initial pressure, we're going to use Dalton's law and add the water vapor and carbon dioxide pressures together to get 150 kilopascals. Then 150 times 100 goes on the left, and on the right we have P2 times V2, where V2 is twice the initial volume, or 200 milliliters. Solve for P2, and we find that the new pressure is 75 kilopascals.